The second conclusion that I hope you can take away with you is that I think we can get really good spatial information about our aquifers that will help us in the long term by understanding better the sedimentary processes that naturally winnow and sort the sediments, and not only tell us about the physical size distribution of the clastic material, but probably about important sorting of the geochemistry and maybe biogeochemistry as well. Where my group is going now is going to continue to look at one of our tasks is to continue to look at aquifer heterogeneity, and we're going to continue to work at multiple scales. So one of the things we want to do is to try to come up with practical methods to characterize aquifer scale, chemical and physical heterogeneity. And behind the backdrop here is a GPR image of the Borden field site. So one of the things we want to do is to work in collaboration with geophysicists and see if we can actually bring to bear on this kind of a problem techniques that are similar to what the oil patch has been doing for years, but in a completely different scale. That is to say, we use a geophysical method, which is non or less invasive, to get a good image of the subsurface and translate whatever that geophysical method is imaging to using reference cores to properties that are important to us as hydrogeologists. We're going to test that next. I have a project to work on that next. At the complete opposite end of the scale, we want to also keep looking at microscale characterization of the sorbent phases and the contaminant interactions. Again, working with Borden aquifer sand is just one example because of the wealth of other transport data that's already available there. But using that information to help us understand at other field sites whether this might be important. And my sense is that because people who study carbonaceous matter in the environment for the purposes of looking at carbon balances have found various forms of black carbon distributed in the environment from the Devonian until now in all sediments, that it probably will be. And then we need to do more rigorous modeling to test all these effects quantitatively. And of course, we do no research, or at least we fund no students to do research with us without support from various agencies. And almost all of this work has been supported by the National Science Foundation with a good chunk of money from the American Chemical Society, what's called their PRF, or Petroleum Research Fund grants, some supporting funding from the Consortium for Solvents in Groundwater at the Waterloo Center for Groundwater Research, and a few scholarships to my students from our local water AWRA chapter and NGWA. And this is to remind me to tell you that I'm now at the University of Buffalo and to invite you to check out our websites. Thanks very much for listening, and I'd be happy to take questions.
Thank you, Richelle. It's very encouraging for students to realize that in 20 years to understand what the first grade is looking at. So we do apologize for the long Ph.D. and master's programs. Or the other explanation is you never get away from the board.
That might be.
So, Richelle, what are your main questions, please?
You're exhausted.
On your heterogeneity field, hydrogeochemist field, how did you plot that field? Basically, how many data points you gathered from the field?
It's about 850.
What's the area of your field?
1.5 meters by 10 meters.
So if you, that data points are graded fashion, or those are all randomly obtained data?
They're obtained from the cores where we have them.
Yeah,
So
those cores are randomly?
no, they're evenly spaced cores, and then the cores are essentially continuously sampled. The only reason for a missing sample is just if we lost a sample or if there's a gap or something like that. So it's 1 meter horizontal and then essentially continuous vertical. So in terms of the error bars on our results, we have very large error bars on the horizontal and smaller on the vertical. And what we find is that when we do look at variogram analysis, for example, of our samples, we get correlation length scales that are not significantly different from what others have found, but our error bars on the horizontal in particular are much bigger than those who have 20 meters of run instead of 10.
Okay, so your data points are spaced for 1 meter. So So how did you get the data points in between those 1 meters? You interpolated or?
There is no data in between them.
Okay, so
That's what I'm saying is that we use a variogram,
Okay, so
we fit a model to that, and then we Krieg in between,
pardon me?
just like everyone else.
No, when you plotted that field, so in that plotting you have only the points where you got the data points. You did not interpolate it or anything.
It is interpolated.
Okay,
It's
so how
interpolated.
you interpolate it? In the traditional radiogram analysis?
Yes.
Okay, so, but if you do for traditional radiogram analysis, you will miss the juxtapositional tendency of facies. You will miss the dipping bed of the facies.
Oh, we took the dip out first. There is a trend in the K field, and we took it out.
Okay, so if you take that K field, that is, what can I say? It is not zonal. It is global angle that that axis will make with the principal coordinate system.
Mm-hmm.
But still you will not get the dipping bed facies of the particular facies. For facies sand, that sand has the dipping bed 30 degree, but in some other places your sand has no dipping bed. But if you take particular angle, if you assume the angle, then that will be the angle for the whole domain. That will miss the angle for that particular zone. So what I mean to say here that is in traditional radiogram analysis, it is my feeling, pardon me, it is my feeling that if you go for this traditional radiogram analysis, then you will miss that dipping bed analysis, dipping bed information, then juxtapositional tendency, and also that mean length, etc., etc. So actually, basically nowadays that Markov chain analysis is coming into picture, and that is more efficient rather than this teaching this traditional radiogram analysis. So, thank you.
You may have found a volunteer to help.
Fine enough. Permeability data is available if you want to do a Markov chain on it. We've tried once. It didn't work very well. But I'm happy to see, as you say, other people who want to work on this data. Very fine. We can learn more things from Borden yet. Yeah.
From a very practical point of view, say you end up in the field, you have a soil sample. Can you recognize if it has a high proportion of hard carbon?
Well, the sad thing is that you don't need a high proportion of hard carbon to have it be important. Remember, even if it's 1,000th as much, it still may be the main sorbent. That's the bad part. The good news, though, is that I think there are ways to, if you think this is important at your field sites, I think there are simple ways to test and see if it's important. So whereas we before have done sorption experiments at just one concentration, all you need to do is do 2 concentrations. You don't need to do the whole range. You do a low one and a high one. And if you see that you get this excess sorption, especially at the low end, then you, in fact, you don't even need to do the high one. You know that it might be important there in terms of your processes. Another anecdote that I can give you as to where it's been, where this notion has already been applied in the field. In Colorado, a colleague from one of the consulting agencies heard this talk and she said, ah, eureka, because she has a setting where she's got, in Colorado they have coal seams that are the source rocks for some of the geological units, and they're pretty well mapped. She had a plume in which a layer above and below the main zone of the plume, she had to put in what she considered to be ridiculously high retardation factors. But she knows that the coal seams are actually one of the source rocks for that unit. And so she said, at least now she would like to maybe do some more confirmatory work on whether that's really the reason, but at least she's got a rational reason for having such a high retardation factor, much higher than you'd expect based on the FOC in the aquifer. So I see some possibilities for this notion to be applied in that way. Yes?
Richelle, has there been any interest in looking at the variation in retardation going from, say, a carbonatic environment to a more acidic depositional environment, particularly center, and the effect on the variable charge in these carbonaceous materials? The reason I ask that is that clays vary with the pH. I guess one of the key materials might vary with the pH and the absorption as a result of that.
The thing is that in these carbonaceous materials, Now, it may be that the availability of absorption sites varies because of deposition of other stuff on top of the substrate in different pH environments. But for the most part, the concept that I'm getting, that there seems to be consensus on, is that it's the hydrophobic sites in this carbonaceous matter that's important. And so if it's the hydrophobic sites that are important, the only reason that the different pH environment would be important is if you have a more aggressive weathering environment. You might have managed to weather away the hydrophobic sites somehow and make them charged. But otherwise, they should not be as susceptible to the pH changes as some other kinds of, like with metal absorption, for example, that's highly pH sensitive in many cases.
I'm just curious, how can you distinguish between adsorption and absorption when you measure?
What I'm using is drawing on studies to model materials and then just modeling the difference in my samples. So I think that's a really great question. And one of the problems is that even in any environmental sample that we choose right now, we find a highly varied mixture of natural carbonaceous matter. And so when I say studies to model materials, I mean that people have either used synthesized char, soot, coke, and looked at that, or we've looked at hard coals and things where we have a pretty good characterization of what's there and looked at what type of absorption behavior you see. And then in my samples, what I'm forced to do is this sort of semi-empirical approach where I'm modeling the behavior as if it's a mixture of two things, a hard and a soft, and also then looking for other indicators of the variability of the organic matter and the carbonaceous matter. So we've done a lot of other stuff too. We've done extractions, then looked at carbon, hydrogen, oxygen ratios and other indicators of the quality of the organic matter. But the petrography, I think, is the most convincing that it's very variable.
One more question.
Do you have direct evidence that shows the hard carbonaceous matter do have the highest, the PC concentrations of the
In these samples, no, but in other samples, it has been shown that the hard carbon fractions do have the highest concentrations of the hydrophobic compounds. So in these samples, we don't have it, but in other environments where you have more carbonaceous matter and enough to separate it, you can show that.
We should probably draw it to a close. I have the customary UW present. We have an additional present. Richelle tells me she's going to be teaching our organic contaminant course. We and I've already got her lined up to teach our course at the same time. But we thought we'd give you a textbook for that course, so it's in here as well. And please